In the last lecture, we reached the 1970s in the history of hydrologic science. The International Hydrological Decade had helped to expand hydrological monitoring networks around the world, to create hydrological agencies and train new hydrologists in many countries. Hydrologic science was going global, not only in the widening presence of hydrologists, but also in the scope of analysis. The concept of sustainable development also received its first major international recognition in 1972 at the UN Conference on Human Environment held in Stockholm. This global perspective and focus on sustainability would greatly influence the development of hydrology over the next 50 years, bringing us to where we are today. Efforts to quantify the global water balance had been underway for much of the 1900s, as shown by these values of the river runoff component reported in studies dating back to 1905. These maps, published by Lvovich in the US IHE Bulletin in 1973, showed the state of the balance at that time. Such analyses were based on full hydrological data where available, and interpolation methods linked mainly to rainfall where other hydrological data were not available. Note that components of the hydrological cycle were mapped using isolines, which differs from the raster or basin presentations we've grown accustomed to today. In his paper, Lvovich wrote that, quote, "It is impossible without maps to study water balance, its geographical features, and the interconnection between its separate elements, to fill blank spaces, and at last to determine water resources of natural regions in separate countries and of the parts of the world," end quote. But what was impossible then was about to become possible. The first Earth-observing satellites were launched in the 1960s and 70s and began generating new global data sets almost immediately. The first GOES satellite, or Geostationary Operational Environmental Satellite, was launched in October of 1975. It monitored the Earth's surface temperature and water vapor fields, including how they varied with altitude and changed with time. 3 years earlier, the first Landsat satellite was launched to monitor the Earth's land surface and how it changed through time. Since these beginnings, there has been a steady increase in satellite technologies and the sensors used to monitor components of the hydrological cycle and related land properties. Satellite observations enabled the indirect measurement of precipitation worldwide, and eventually evapotranspiration and even river stage using satellite altimetry. Numerous data products are now available and widely used by hydrologists. Landsat's multispectral scanner enabled mapping of land cover with a pixel resolution of 60 meters and monitoring land cover and land use change over time. Landsat was also useful in monitoring the changes in size of lakes and wetlands, and even the extent of flooding along major river channels. Next came breakthroughs in computer-based hydrological modeling made possible by the growing capacity and availability of personal computers. The groundwater flow model MODFlow and watershed model HBV are examples of models originally appearing at this time. Both have since grown in capacity through many versions. Such hydrological models, and many more, enable hydrologists to apply the well-established quantitative theory of hydrology to simulate hydrological phenomena across space and time. Models are used to fill gaps in measured data records, to estimate hydrological processes in ungauged basins, to forecast water availability or extreme events like floods and droughts, and to explore future scenarios influenced by a wide variety of changes underway on the planet. During the 1970s, there was a major shift in the perceptions of people around the world toward human impacts on the planet and the consequences for our long-term viability. Concern was growing over the pace of population growth and related demand for natural resources. In arid and semi-arid regions, it became clear that growing demands were leading to water stress, which was likely to become worse and spread more widely. Severe pollution of water and air resources was recognized and led to the creation of new environmental agencies in many countries. And on the top of Mauna Loa volcano in Hawaii, far from any sources of air pollution, scientists were recording a steady annual rise in CO2 concentrations that were understood to represent a CO2 increase in the atmosphere of the entire planet. In September of 1972, John Sawyer of the UK Meteorological Office published one of the first papers highlighting rising CO2 levels and explaining the potential consequences for global climate. His data extended only to 1968. The curve looks like this today. As scientists focused more on global Earth system trends, they found rising CO2 was just one of many. Other greenhouse gases like nitrous oxide and methane were also rising exponentially. On the land surface, tropical forests were disappearing, domesticated land expanding, and overall degradation of the terrestrial biosphere accelerating. The combination of these trends over the past 200 years is regarded as the Great Acceleration, and it is, of course, linked to accelerating socioeconomic trends, where we see the population growth curve, as well as curves showing the increase in the number of dams and growing water use. Impacts to the water cycle and related feedbacks on socioeconomic conditions are found in many of these trends, which means hydrology is central to addressing their negative impacts. The turn of the century was a monumental moment for countries around the world, prompting the international community to review the state of the planet and make collective commitments to addressing major global challenges, including the environmental crisis. By the late 1980s, considerable research had progressed on climate change, and global concern had grown. So in 1988, the United Nations Environment Program and the World Meteorological Organization established the Intergovernmental Panel on Climate Change, or IPCC. The initial task of the panel was, quote, to prepare a comprehensive review and recommendations with respect to the state of knowledge of the science of climate change, the social and economical impact of climate change, and potential response strategies, end of quote. Since its creation, the IPCC has published 5 assessment reports, which have documented our growing knowledge of climate change and strongly influenced international cooperation and actions to address it. In 2001, the UN also initiated the Millennium Ecosystem Assessment with the objective of assessing the consequences of ecosystem change for human well-being and the scientific basis for action needed to enhance the conservation and sustainable use of those systems. The findings were published in 6 synthesis reports, one of which focused on wetlands and water and strongly influenced our view of aquatic systems and the ecosystem services they provide. Also in 2000, the UN launched the Millennium Development Goals, or MDGs. There were 8 goals, and Goal 7 on environmental sustainability included the target of, by 2015, reducing by half the proportion of people without sustainable access to safe drinking water and basic sanitation. Water was integral to achieving other Millennium Development Goals as well, related to food and energy production and health. All of these international initiatives stimulated research and applications inside the hydrological community and helped orient efforts worldwide to address these pressing international challenges. They also influenced the hydrology program at IHE Delft. Recognizing the central role of water and hydrology at the interface of numerous disciplines working to address the growing global challenges, IAHS launched a new international initiative to energize and focus international hydrological research in the decade from 2003 until 2012. The primary research objectives of the initiative were to improve the ability of existing hydrological models to predict in ungauged basins with reduced uncertainty, and to develop new and innovative models representing the space-time variability of hydrological processes, and thereby improve the confidence in predictions in ungauged basins. IAHS recognized that hydrologists, with all we had learned about hydrological processes, still lacked a sufficiently strong scientific basis to provide reliable predictions of water availability in the majority of smaller basins around the world that remained ungauged and were not likely to be gauged. Overcoming this knowledge gap would require improved hydrological theories, models, and empirical methods. The outcomes of the pub decade, both research results and its impact on the hydrological community, are detailed in the 2013 paper by Harakovich, which is one of your readings in the course. The two most recent sub-disciplines of hydrology I'd like to mention are ecohydrology and sociohydrology, beginning with ecohydrology, which emerged first. Ecohydrologists are concerned with the dynamic interactions and feedbacks between the hydrological cycle and ecosystems. A large number of ecohydrologists are primarily focused on the linkages between climate, soil, and vegetation, concentrating especially on the soil-moisture balance equation. As part of UNESCO's International Hydrological Program, a broader concept of ecohydrology also emerged that extended to all components of the hydrological cycle and connected more strongly to water resources management, beginning on the landscape, extending along river corridors, and reaching estuarine and coastal systems. While human influences on the hydrological cycle have been noted throughout the history of hydrology, the subdiscipline of sociohydrology and its focus on the dynamic interactions and feedbacks between water and people emerged only in recent years. Sociohydrologists probe much more deeply into these dynamics, considering how the availability of water or protection from its hazards accelerates socioeconomic development in, for example, an economic population loop, and how continued growth along this loop leads to increasing community sensitivity over related environmental degradation or negative social impacts. Sociohydrology is still in its early days and is developing rapidly. The review paper by Pandey and Murugesho is available for you in your readings if you'd like to learn more. Okay, so that brings us to today. But what about the future when your contributions to hydrological science and water resources management will be more strongly felt? Perhaps you'll choose to focus your professional attention on research to further investigate and improve understanding of hydrological processes. IAHS continues to provide leadership in the hydrological community and facilitated a process to identify 23 unsolved problems in hydrology that the association wishes to encourage research into. We don't have time to go through all 23, but I'd like to at least mention the main categories of questions and an example from each. I've included the paper describing all 23 in your readings. The first category of questions is time variability and change, including key questions about whether the hydrological cycle is accelerating or decelerating under climate and environmental change. Under the category of space variability and scaling, there's the perplexing question of why streams respond so quickly to precipitation inputs when tracers show that the water flowing from hill slopes into streams is often not from the current precipitation event, but older water. Considering variability of extremes, there's the question of how flood-rich and drought-rich periods arise. Are they changing? And if so, why? Interfaces remain important in hydrology, with one of the questions being what factors contribute to the long-term persistence of sources responsible for the degradation of water quality. New data sources are appearing, such as citizen monitoring, but hydrologists are asking what is the relative value of traditional hydrological observations versus these new soft data sources. There's still a great deal of progress to be made in modeling and the question of how hydrological models can be adapted to be able to extrapolate to changing conditions. And finally, hydrologists are concerned about interfaces with society and questions like how the uncertainty in hydrological predictions can be communicated to decision makers and the general public. I hope you'll delve more deeply into these questions by reading the paper and consider them in the design of your own research, whether that be in an MSc thesis at IHE Delft or elsewhere. If your professional interests lie more in the applied aspects of hydrology and linkages to water resources management, there will certainly be priority issues in your home country that your MSc program and especially your thesis research project can be oriented towards. Internationally, efforts to improve water resources management are organized within the framework of the United Nations 2030 Agenda and the Sustainable Development Goals, or SDGs, which superseded the Millennium Development Goals, or MDGs, in 2015. As with the earlier MDGs, water is important to achieving many of the 17 SDGs, but issues related to water are focused under SDG 6, which is to ensure availability and sustainable management of water and sanitation for all. There are 8 targets under SDG 6. The first 2 focus on providing safe water for drinking and sanitation. Target 6.3 focuses on water quality and 6.4 on water use efficiency. 6.5 is a target to implement integrated water resources management at all levels, and 6.6 is focused on protecting and restoring water-related ecosystems. Targets 6A and 6B are special in that they're means of implementation targets focused on international cooperation, capacity building, and participation of local communities. In other words, they're targets to assist in achieving the 6 outcome-based targets above. To learn more about SDG 6, follow the link on the screen. A new phase of UNESCO's International Hydrological Program has also just begun, and as an institute under the auspices of UNESCO, IHE Delft is committed to participate in this program. The main topics relate to research, education, and management, with an emphasis on global change. This new phase of the program runs until 2029, which is closely aligned with the 2030 completion date of the UN's SDG program. The efforts of UNESCO IHP and IHE Delft will certainly be designed to contribute to both of these important global efforts. So, that brings us to the end of our 2,000-year journey from the ancient beginnings of a natural philosophy of water cycling in the land areas of the earth, through the early development and continued refinement of the scientific theories and applied practices fundamental to hydrology today, and the global goals and unsolved problems hydrologists will be addressing over the coming decade. In the next topics of this preparatory course, you'll gain more knowledge and skills on the fundamentals of hydrology and water resources, the catchment approach, major drivers of hydrological change, and an overview of data, tools, and modeling. Thank you for your attention in this topic. I hope it will be helpful to you in your future studies, potentially here with us at IHE Delft.